Hello, this is Dr. Strickland. In this video, we will investigate the acidity of an alpha hydrogen and ketoenol tautomerization. Take a minute to read through these student learning objectives. These are the things you should be able to do by the end of this video so that you're ready for the things we will do together in class. So we start with the problem. Using the reactions that you know so far, is it possible to transform cyclohexanone into 2-cyclohexenone? So we'd have to be able to do some sort of elimination reaction. And it's not set up for a Wittig reaction. So we need something that would involve an alkyl halide or an alcohol at the alpha carbon, the carbon that's just adjacent to this carbonyl. But the only way we know to install a halogen so far is with radical substitution, and you couldn't make it choose this position over this one over this one. So at this point, it's not possible, but it will be possible pretty soon. So it turns out that this is based on the acidity of alpha hydrogens. A hydrogen atom bonded to an sp3 carbon that is adjacent to a carbonyl carbon is much more acidic than hydrogens bonded to any other sp3 carbons because the conjugate base is stabilized by resonance. Remember that an sp3 carbon that's adjacent to a carbonyl carbon is also an allylic carbon. And so that would be a handy thing to remember. So if you look up the pKa of alkanes, and I've got propane here just as an example, you find that propane has a pKa of about 60. They are very, extremely weak acids. They have no interest in donating a hydrogen cation. But with a strong enough base, you could convert it into its conjugate base. And if we did that, we would have this guy here. Now, this new non-bonding pair of electrons is localized. It has to stay on that carbon. And because of that, it's much less stable than the other ones we're going to look at that have resonance contributors. It's localized. Must stay on one carbon. No resonance contributors. To help stabilize it. Okay, so if you come down here and compare, say, an aldehyde, and we've got same kind of situation, we set it up. Well, this shouldn't have that hydrogen there. Let's take that out. Going to remove the hydrogen cation and create the conjugate base. And at first, that new non-bonding pair of electrons is just on that carbon. But it doesn't have to stay there. Unlike the situation above it with an alkane, this guy can be shared. It's like having a friend to help you move a heavy box. If you can delocalize that new pair of non-bonding electrons, you'll stabilize the whole anion. If you stabilize the conjugate base, what does that do to the acidity of the conjugate acid? Well, if it's going to a more stable conjugate base, then the conjugate acid is more willing to donate a hydrogen cation. And in fact, if you look up the pKa of an aldehyde, it's 17. That's a lot more acidic than an alkane. In fact, it's 10 to the 43 times more acidic. That means that's crazy much more acidic. So the new non-bonding pair being delocalized is what accounts for this. So now we've got the new non-bonding pair delocalized over 3 atoms. Okay, well, let's take a step. What if we had a situation where we had a methylene group, a CH2, that's alpha to 2 different carbonyl groups, excuse me. All right, so we've got a base. Remove a hydrogen cation. All right, so I want you to pause the video and draw what this looks like. What does the conjugate base look like at this point? Pause the video and draw it, and then come on back. All right, welcome back. So, when this first is formed, we've got the new pair of electrons in the negative charge right there on that carbon that's between the 2 carbonyl carbons. But it doesn't have to stay there. All right. So pause the video and draw a resonance contributor for this guy, kind of like you did above. Do that and then come on back. All right, welcome back. So you could have chosen to go to the left like this, or you could have chosen to go to the right. And it doesn't make any difference at all, because we're going to get to the second option here in just a minute. All right, so if you went to the left, the delocalization looks like this. And remember, when you're drawing resonance contributors, the atoms never move at all. The only thing that moves is non-bonding electrons and pi electrons. Okay, so you see we've got, at this point, the new pair of electrons delocalized over 3 atoms. See, above here with propanol, we're delocalizing over 3 atoms. And at present, that's what you see here. But in fact, there's another option. You could have gone to the right. Now you can either come back here and do it again, but just go in the other direction, but then you'll have a whole bunch of arrows on one structure. You can do this. And draw a third resonance contributor that looks like this. So the fact that we can delocalize it in 2 directions means that, in fact, this new non-bonding pair of electrons is delocalized over all 5 atoms. All right, so if your non-bonding pair of electrons is delocalized over more atoms, then it will be more stable. If the conjugate base is more stable, then the acid should be more reactive. It should be a stronger acid with a lower pKa. So there is a table, table 17.1, and I want you to be familiar with this table. And over here in the left-hand column, you see the pKa that has to do with losing the alpha hydrogen for an amide, an ester, a ketone, an aldehyde. Here we've got a nitrile. Let's skip this one for a minute. This is a nitroalkane. And you can see that as we're going down these 2 columns, that the pKa's are dropping, and that means that the compounds are getting more acidic. The other thing that's in this table are the compounds that have one of these CH2s that's sandwiched in between two of these carboxyl groups, carboxylic acid derivatives, ketones, aldehydes, anything involving a carbon oxygen double bond. And so we've got two nitriles, we've got two nitro groups here. If you go over to the far right-hand column, you see there's one with two esters, one with an ester and a ketone, one with two ketones, and then this bottom one here, which is a ketone and an aldehyde. Okay, so the one that we're dealing with right now has the two ketones. That's 8.9. So this compound is more acidic. It's more willing to donate a hydrogen cation because the conjugate base is more stabilized by resonance. All right, and we're going to see that as one of the big themes in this chapter. The other one has to do with keto and enol tautomers, and we've seen this before, but it's going to come up in a little different context this time. So tautomers are constitutional isomers that are in equilibrium with each other. Keto-enol tautomers differ in the placement of two things: a hydrogen atom and a pi bond. And in general, the keto isomer is going to be more stable than the enol isomer. As you read through the text, you'll see that there are cases where the enol isomer is more stable, but there are specific structural reasons for that. So with the keto isomer, all of them are going to have a carbon oxygen double bond. But it doesn't have to be a ketone. It can be a ketone, an aldehyde, or any carboxylic acid derivative. Now the enol isomer is labeled such because it has an ene, a carbon-carbon double bond, and an ol, an alcohol. And you can see that they share a carbon right here. When an enol, that is always true. Carbon-carbon double bond and an OH. They share a carbon, and the carbon-carbon double bond links the alpha carbon and the former carbonyl carbon, the carbon that was in the carbon oxygen double bond. Okay, so these are the two big things that we're going to trace in this chapter. Take a minute and answer the question at the end of this video, and then come on back.